This lecture will introduce graphic statics and we will start from the very beginning, building progressively all the concepts and application of graphic statics. This will be important since we want to be able to reproduce by yourself all these processes and be really understanding the essence of the application that I will be presenting at the very end of this presentation. We will introduce briefly, but we will not cover 3D graphic statics that will be detailed in the next lecture. Indeed, 3D graphic statics with the vectorial approach, that is the approach that we have been chosen, opens the problem of graph being not reciprocal, so requiring specific strategy for constructing the force polygon. So force polygon will be introduced right now. And let's start with the lecture. We are currently here in Belgium. This is 12:09, and I will start with the topic of this lecture. So I will start first by introducing some typical use of graphic statics. Then I will be back to some historical benchmark that you know already with a presentation that your professor made some weeks ago. Then we'll enter a question with vectorial equilibrium and solid static, in which we will take the problem of triangle of force according to Stevin. This is 1605. Actually, Stevin van Brugge is in the actual Flanders that's situated in Belgium. So we have a link with the very beginning of static graphic. We'll discuss equilibrium with three forces, internal forces with graphic statics, then moving to timber framework analysis with graphic statics. Then we'll go to arches and funicular polygon, in which we'll be discussing parabola, application of funicular polygon, geometry of arches and vaults with graphic statics. We'll go to vault analysis and some additional consideration about masses and equilibrium in structural design. With this, we'll be ready to move to beam analysis with graphic statics and to truss analysis with graphic statics. Later on, we will address the topic of hyperstatic trusses with graphic statics, as well hyperstatic rigid frame with graphic statics. We'll have some word about 3D graphic statics and then moving to applications. So we'll have a contemporary exam that will be the Traversiner steg from Jörg Konzett, and the classical example with graphic staging according to Maya, so Robert Maya, on which my PhD was the topics. So let's move to this with typical use of graphic statics. I'm just moving this for me to be ready, and that's right. So let's go. Typical use of graphic statics. One of the main concepts that we will be meeting will be the concept of truss line. The concept of truss line has been introduced at the very beginning of the 19th century. And here you will see the proposal from Mary in France. You have Gerstner in Germany, and another contributor in England, and this will show you what would be the minimal and maximum truss into arch, and it will be a truss a tool to address the question of stability of arches. So each of the example you have on the screen are using graphic statics and the theory of truss line to address the stability of arches. We'll have to discuss about stability and the concept that are related to, and we have to discuss about plastic design, but this will be for the second lecture that we will have next week. So about static graphics, you can see here the principle of taking a mouse of truss line. Here you have the principle of funicular polygon here, or force polygon here, and the equilibrium of three forces that will be addressing just in the next slide of this lecture. Another example is here the theory of truss line as applied to hinged concrete arches. So this has been applied, of course, to stone masonry, but also to masonry bridges with bricks or with stones. And here this application is from Robert Maillard again in a bridge of 1905, in which you can see in the middle of the screen the trajectory of the jet linear for Eigen qubits. So it means the truss line for the self-weight, dead weight. And you see all the typical element of the characteristic analysis in graphic statics. You will see also that the utility is to make measure about some reference to get the difference of the position between the drop line here, so the truss line, and the line that will be gathering the level of the center of gravity. That will deliver directly the bending forces, and we will analyze this. We will be analyzing this in the next slide. This enables you also to make the calculation about the reaction force, their direction, and the composition of the self-weight of the support foundation. This picture coming from this bridge, this is the first very complete bridge, the kind of 3-hinged arch bridge made of concrete, as designed by Robert Maillard. You have another example of original drawing coming from Robert Maillard, and here you can see that the truss line as a funicular polygon is perfectly fitting the geometry. I must say that it's not fitting the geometry, but that the geometry is perfectly fitting the axis, the direction, the line of the truss line. So this has been used as a tool to define what should be the geometry to have only compression force all along this bridge. You can do also another use for graphic statics. For instance, if you have graphical construction to define where the center of gravity of specific section and where will be the moment of inertia according to two directions for this part of a tunnel having water into it. As I mentioned, you can measure the deviation between the level of the truss line here in orange and the level of the center of gravity that will give you the information about the bending occurring into the structure. I will detail this further. You can also do bending analysis using graphic statics, but on very complex system. Here you have a portal frame system, so with two legs and two overhang on both sides. And I will explain you in the main line how to use graphic statics for analysis purpose into this. It won't be truly designed, but well for analysis. Then you can use also graphic statics to analyze deformation of systems. Since graphic statics is a kind of mathematical integration, you are able to calculate from forces, the bending forces. You can from the loadings calculate the bending forces through a funicular polygon. And once you use again a funicular polygon on the previous funicular polygon, we'll get another figure that will be representing the deformation of the system. Of course, you can analyze trusses as on this example of the scaffolding of the Saginatobel Bridge. This principle will be introduced by Cremona that I will be presenting just after this. And this was the scaffolding of this bridge that was presented here. Actually, this is a variant for the scaffolding, but anyway, this is the same kind of calculation. So let's go to some historical benchmark for graphic statics that you know already. You know that a long time there has been procedure to assess the stability of arches, mainly as the most complex system at that time. And we are here in the very beginning of the 17th century, at the very end of the 16th century. And we see that one of the first that will proposing something that will go in the direction will go with truss line will be Leonardo da Vinci, while he will proposing using for assessing the stability of pointed arch, he will proposing using a kind of how to say so, the line that will be joining, the rope that will be joining the end of the arch will not cross the inner arch, and it will give you the first technique to assess the stability of arch. Moving from this, if you are looking to timelines, you can see that there are developments that are specific for the two lines about arch theory that will be connected to graphic statics. You will see here in the third line, the third timeline, the development of graphic statics. You can make a link with what will be taught in engineering school and architectural school. And at the end, there's a link with plastic design that will be established later. The fact is that the two approaches of the assessment of arch theory, the collapse approach and the kinematic approach for equilibrium, have to be combined to assess surely the stability and the safety of arches, and the justification of this will only be given with the principle of plastic design from very late in the history. Actually, this is Jack Eyman that will be providing the demonstration using a plastic design of these two approaches in 1969. So to enter into detail, you see that Leonardo da Vinci, that will be the first that will be tackling the question of the arch theory, as it will be the first one also to tackle the issue of the beam assessment. And you will have to wait a long time before another researcher, Bernardino Baldi, in 1621, 1 century later, to enter into this question. The first contribution will be about assessing what's happening in an arch when we have a collapse and a mechanism that is appearing that will be to collapse. So you will see a very famous contribution to people that will be teaching in the School of Architecture in the first time in blue, in light blue, and School of Engineering in the second time. About the question of equilibrium that is central to the question of graphic statics, the first one will be Hooke, then you will have work from Gregory and Pollini, this famous analysis on the arches from Roma that will be presenting later, to arrive to proposal from Gerstner, Mosler, and Méry. Gerstner in 1831 in Germany, Mosler in 1833 in England, and Méry in 1840 about the truss line theory. And a link will be made with Méry and Barlow to graphic statics and the use of funicular polygon. So you see that the technique exists, let's see, at the beginning of the 19th century. About graphic statics, the first one will be Simon Stebin von Brugge, so in the north of the current Belgium, that will be addressing the question of equilibrium with three forces and also using weight to stabilize construction. Of course, when you are using arches and vaulting in architecture, the main problem to stabilize them will be a question of weights and the distribution of weight to get an equilibrium. Some later, nearly 8 years later, you will have French Marc Varignon that will be demonstrating all these applications that have been founded by Stevin. And then this work will be taken over by Poncelet. I will present this more in detail, getting to some engineering application. You see that engineering school appeared as early as 1716. Before that, this theory were taught in School of Architecture. The first one was in France in 1671, and the first School of Engineering was the School of Ponts et Chaussées in Paris, founded by Perronnet. From there, we'll be entering the era of engineer and the wide structure. And you see that Poncelet is taking part of this adventure, and he will have a pupil that will have as name Kuhlmann. Kuhlmann that will be founding officially the static graphic with his book of 1866. Of course, Maxwell will be there just before, and he will be investigating also 3D graphic statics as early as 1864. From then, you will have classical contribution for Cremona, Bohr-Lévy, and so on that we'll be introducing later. So you see that, for instance, Karl Kuhlmann was one of the first generation of teacher at the Polytechnical School of Zurich, founded in 1855, and Kuhlmann will be publishing his book in 1866. So let's move to more detail about the contribution. So the first one will be Stefan von Brugge. You will see appearing the first equilibrium as a triangle of force and the first funicular. So he established this on several problems, but it will be the Frenchman that will be demonstrated in a rigorous way, and we'll see appearing the concept of the parallelogram force that will be a kind of generalization of two triangles as used by Stefan. And of course, you will see the demonstration of the first funicular line. Later on, Victor Poncelet, as is explained, that will be the follower of Gaspard Monge, that will be invented the descriptive geometry. And with this graphical environment, Poncelet will apply it to a series of problems. The follower will be Karl Kuhlmann, that will be professor in ETH Zurich, among others, and that will be publishing this book in 1866 about the graphicstatic in German. You have a pupil, his name will be Wilhelm Ritter, that will be publishing the application of graphic statics and also addressing the question of hyperstatic structure. The history is that Wilhelm Ritter will become professor after Kuhlmann and will have a pupil, his name will be Robert Maillard, and that I will present some use of graphic statics for design purposes. There will be a parallel development with Luigi Cremona that will be proposing a full graphic method for solving trusses that Kuhlmann will not be inventing. So his name will become famous was this kind of a very graphical diagram. About 3D graphic static, researchers are initiated as early as 1864. First, actually, they will be initiated in the same time by Rankine and by Maxwell. So Rankine will take the question with the polyhedron-based approach and will be later developed by Maxwell in 1867. And on the other side, Maxwell will be addressing the question in the same year of 1864 with the vectorial approach of graphic statics. That has been the approach we'll be following in the team and for all researchers. So graphic static will be widely used from the book from Karl Kuhlmann in 1866, the Graphicstatik, and will be used for more than 1 century. It stops where you have the computer arriving and the pocket calculator that will be the preference to analytical or numerical methods. So at that time, around 1970, School of Engineering will progressively stop to taught graphic statics to move to other question. But so at the middle of the year 19, they will stop with teaching this. But some year later, there will be a comeback of graphic statics, not for question of analysis, but for question of design. I will make a clear difference for this later on the slide. So this is part of a context in which you have a graphical approach, in which you have slide rule also. And as you can see here on the first pages of the book from Karl Kuhlmann, you have, for instance, a graphical drawing that are made to calculate the exponentiation and multiplication on the right. So that's the context in which graphic statics appear. So Let's move to the question of vector equilibrium and solid static. We will be back to the very first concept, so the notion of vector. Vector is a kind of arrow that have a direction, that have a start and that have an end. The length will be providing the information about the magnitude of the force that will be applied onto this. Of course, to use graphic static, you will have to draw this vector at scale, so you will be able to measure physically what will be the length of this vector to get the value of the force that are involved into this. There are three very simple principles that will be met about graphic static. The first is the principle of inertia, as proposed by Kepler. If you know Kepler, he will show what will be the moving of the system from planets around the sun. And the first principle is that nothing won't move as a point if you have no force that will be exerted to this. The second principle will be the third law of Newton, about the principle of action equal reaction, as you can see here, with the load applying a force on the ground, there will be the same reaction that will be pushing upwards. This is the third law of Newton, the first law being the principle of inertia, and the second being the law of acceleration. The third law that we'll be using for graphic static is a principle that if you have several forces acting on a point, you can replace all these forces, the black one, by the resultant that will be designed here in blue, and just manipulate the resultant forces. To get the resultant force, you can have a simple construction that will be based on just adding this vector to have the resulting force. So the start from the first will be arriving to the end of the second to get what would be the resultant. Of course, you can do it algebraically also. So the principle of balance of point will be that if you have a point that's not moving, on the other hand, you can have no force applying to this, but the other hand, you can have also a series of force that will be constituting a closed circle of force, so the start corresponding to the end, and it will be demonstrated that the system is equilibrium. That will be the main objective for a series of structure. To apply graphic static, you will be a long time using solids. So the definition of solid is that a volume that won't change of a dimension when you apply force to it. This will have a consequence that you can apply the forces anywhere along its line of action. And pulling on one side, on pushing on the other side, will have the same result in terms of equilibrium. To guarantee equilibrium in the plane, you have three conditions to fulfill. You have translation condition on the plane as X translation and Y translation, and you have a rotation that can be involved in the equilibrium. So we'll need at least three components of reaction force or three force to stabilize the system. So with graphic static, you are able to use this force with their line of action. And as soon as you have a closed cycle here, you are able to demonstrate the equilibrium in translation in X and in Y. And as soon as you have this line of action of the forces that are applied to the system that are converging to a unique point, you will be guaranteed the rotational equilibrium. When you have a system of parallel force, things are slightly different. You can show that this is a closed polygon. Actually, I'm supposed to represent them here, but you cannot see anything. So I will use this method. And to demonstrate the equilibrium, you will need another tool that will be the funicular polygon. If you are going to 3D, you have three possibilities on translation and three possibilities of rotation around each of these axes. But most of the time, you will be able to simplify a 3D problem into a 2D problem. And that will be the topic of this lecture, in which we will be addressing the question of 2D graphic statics. So let's move to the triangle of force according to Stevin. Stevin will demonstrate this using triangle and slope of this triangle showing that will be a proportion between the loads that will be equilibrated and the length of the side of the triangle. So this being proportional to this and this being proportional to this. It can do it with this very particular rectangle triangle, but it can do so also with varying this about proportion. This will be the first polygon that will be drawing on the system with conversion forces, and we'll see appearing progressively more and more complex approach onto this. So this drawing are coming from the book of Stevin from 1605, for they are more than 400 years old. And this is coming from the book. Of course, about the triangle of force of Stevin, you will be able to make it in different way, leading progressively to the parallelogram force. Actually, the principle of parallelogram of force will be put forward by Newton, showing if we have a force that will be applied to a small boat that is crossing a river with the flow is this direction. If you want to have the resulting direction, you can build this parallelogram of forces. This is a kinematically approach, but so to demonstrate it, but to demonstrate this triangle of force, Stevin will just use the statistical law, and that will be something important. So you see here Stevin that's going on applying to several problems. And what's happening as soon as you have not three forces applied to a system, to a point, so the point is here in the middle, but you have four forces. You can see that in this case, you can build several polygon of force polygon that will be all correct, and you won't be able to define this if either you decide what would be one of these forces, or either will be considering the deformation of each of the elements constituting a system, and will drive you to deformation of system in the last part of the lecture. So let's be back to this aquarium with three forces and with the first application. If you have a stone that are just lying on the stone wall and you're looking to the equilibrium, you will use the weight of the stone placed as the center of gravity, this way here, and you have to draw the line of action. As soon as you know the direction for the stone walls will be horizontal, you will get an intersection point between this line of action and this line of action. If you want to guarantee the equilibrium, you have to pass with the third force through the material contact with the ground here and to this point, and you get the direction of the line of action of this line. And as soon as you have the direction of the three forces, you are able to build the force polygon here and demonstrate the equilibrium. That's very simple, but you will see that there are very interesting application to this. If you have not force aligned, you will just have a system that will be rotating, as for instance, here on the wheel. You can generalize this system. If you have two systems, this is symmetrical, so you can cut it in two parts, having the same kind of resolution. You can complexify progressively the system, just considering the weight that is resting onto the two support flat stone below, and you can make the distribution as early through the point of contact here and here, building the first force polygon. Going ahead, if you are just not going outside of the stone, you have to be more precise about the way that thing will be designed here, and you see the force polygon getting more and more complex. I can go ahead with this using the wave from the supporting stone and having the same kind of resolution. I can do also the same with progressively splitting the wave into its component to have the first arches that will be appearing on the system, and that will drive you to the principle of funicular polygons, as we can see later on. So the first application, maybe this famous bridge of Robert Maillard as designed in 1929. And actually, if you seek for the equilibrium, as I will be demonstrating later, you have a symmetrical system with a horizontal thrust line here equilibrated with the resulting applied forces. And you know here from this point of intersection and from the center of the hinge, what will be the direct direction of reaction force that will enable you to make the calculation. I will show this in detail later on. Let's move on a question of internal forces with graphic static and taking the example of a domain. So this is a huge stone resting of two stone pillars on each side. We're just considering the weight of the stone above from the resultant apply at the center of gravity. And you can see that you have to connect point. You have to connect connection here, this center of gravity here. So you will be knowing what will be the trajectory of force. It can be tell that this is a kind of thrust line. About decomposing the equilibrium, you can see that just resting on the analysis with the first term and getting the equilibrium above, you are able to decompose very quickly to this. The resulting is that the force you get here on both sides to be equilibrated to another direction here, and you won't be able without adding a horizontal component onto it. And you can assess what's the value using again a triangle of forces, and it will demonstrating that since you're not able to push here toward the node, you will need an internal force that will be appearing in the system. So demonstrating what's happening in the system. And indeed, you have the traction force that could lead to a break into an arch as here. So let's move to timber framework analysis with graphic statics. You have one of the first system as being this timber framework from the Basilica of St. Paul. I will be neglecting all the support here since they are just here to stabilize the form here. The two stiffness will be deployed by this line and the horizontal one. You are able to make equilibrium, and we will be introducing progressively what will be the solving of the system. You know intuitively that will be compression and traction below. What's about solving this? For this, let's simplify the system and going to a very simple triangle. We'll be using the Bose notation I introduced in 1874, in which you are just writing capital letter in between each of the four that will apply to the system. And as soon you will have this done, each force will be named from the capital letter between on both sides. So this will be the vector named AB, so going on the force polygon from A to B. And the next will be the vector going from B to C and so on. If you have a closed panel, you have to write a number into it, and this number will help you to give a name to this bar that will be called B1 or 1B, depending the sense you will be reading at the name of the force. So about this, you will have to take a convention, and our convention will be to give the name clockwise, as later we'll be reading the force as clockwise. So about this, you can be building the line of loads on the right that will be constituting the force polygons, so going from A to B and so on, building the first line. You have the reaction that will be symmetrical, and we have to put somewhere in the middle, so it's supposed to be superimposed. And number E at the mid-length of the resultant forces, and that will give you all the name of the forces. So force A, A will be here from E from A on the side of the system. This system is not finished yet. You need to assess what will be the force in each of these members. And you know that the direction of the vectorial force have to be parallel to the system, as indeed we are considering only hinged systems. So the only force you will get in the system will be a compression force along the bar. So you know that you're looking for a number here that will be 1, and 1 will be common to B1 and to C1. You know the direction of B1 and you know the point beam, so you are able to draw this line. And you can do the same also for C, getting this intersection point here. This is 1. And what is wonderful with graphic static is that it will enable you to check this system, since you have still a bar that has to be drawn, and you have two conditions have to fulfill. The first is that you know this the orientation of this bar, this is horizontally, and the second is that you have passed to 2 points that are 1 and E. And actually, the solution is not always met, but in this case, you can see that the orientation will be horizontal and passing through these 2 points. And that gives you the opportunity to check that the system is well solved and will be in equilibrium. And that's one of the main advantages of graphic statics. About discussing what would be the forces, you have to read this force by turning around some nodes. And from this, you will be reading the name of the bar from each side from B to 1, and B to 1 will show you that will be pushing on this support on each side. That will be demonstrating that the bar is pushing on the node. On the other side, you will do 1 to B pushing in this direction. So the bar is pushing on the nodes by reaction. Second principle, you have to know that will be pushing on the bar, and this bar will be in compression. You can do the same exercises for each of the bar, and you won't be making mistake about this and getting the result. Of course, you know that the force polygon is the representation of force, so you can measure each of these bar, and you can have a look directly on what will be the length, let's say the proportional length of each of these bars to see where are the main forces. You can do it managing more complex system. The fact is that when you are using this kind of framework, even if a force are applied somewhere else, you have to put this force only on the node of the structural system. So you have to transfer this force with the node applied to this. You will see that in this case, we have more than one closed panel, and you have a series of forces that will be appearing with more and more force polygon. So this is the constructed force polygon, construct in the same way. I won't detail it, and you can do exactly the same analysis showing which bar are compressed and which bar are stretched in tension. You could say that actually this is easy to guess what are the forces. For instance, here you have a bar force that are applied in the middle. If you push here, you are not able to system the system without this, so we'll have compression on both sides. This compression has to be equilibrated by tension, and here with this force we'll need 2 bars to equilibrate it. If you are pushing this direction, we'll need this bar in tension. So that's easy to say in this case, but that won't be that easy for more complex system, for which we need analysis. For instance, for wind forces applied to a system, you will have to take into account forces that are applied perpendicular to the faces of the roof. And in this case, you will have to consider what will be the reaction force. Indeed, what we know with graphic statics will give you some tools to assess what would be the reaction of force. The only thing you know is that due to the type of support you choose here, you will have a vertical reaction. And so all the horizontal reaction will be sustained by the support at the right of the screen. So for having the resultant force, you will need to use a funicular polygon that I will introduce some later on. So I won't be detailing this. We'll just replace the system by 2 forces. So this is the resultant of the force applied on that side, and this will be the resultant of the force applied on the other side. From this on, you are able to start building the equilibrium of the 3 forces, 1 force, 2 force, and the last one will be corresponding to the sum of reaction force. So I take a parallel to this line here and a parallel to this line here, having a resultant this line. And you know that this line has to be decomposed in a vertical force on the left and a horizontal force on the right. To position all these forces, that's very easy. You know that the resultant applied force are supposed to have an intersection point here. You know this direction, and so from this here you will know the intersection point with the vertical force. This intersection gives you the direction of the last support forces. I was decomposing it here, but I don't have this information at the very beginning. I have the resultant forces here. I know this vertical, and this intersection here will give you what will be the rotation of forces. So you see the first principle are applied to get the result forces. So we know this time what would be the direction force on the right, and we can start building what would be the cycle of the line of load. So the load line will be here, it will be broken these times, and this is close with the reaction force that are shown here below. We can move again with adding the other bars and with parallel of each of these bars. For instance, if you have C2 here, you know C, and you have 2 appearing here as an intersection with the vertical passing to 3. And this is an incremental construction that you are able to do. Of course, the same applies in deciding what would be the several forces and their direction, and what would be the main magnitude of force. You could say, well, of course, I could guess that this bar will be in traction here, and that will remain in compression. So again, solving the system. Okay, so let's move to another system with asymmetric loading. This is the kind of system you have on framework and pushing with 2 bars here. And you have to assess first what would be the reaction forces. So using the principle of the equilibrium of bending forces, you will be able to get the result of forces as applied here. So you put the bar somewhere here, you make the equilibrium around this. You have this form acting with 1 lever arm, second force here acting with a second lever arm, and third reaction acting with third lever arm from here to here, and you get the value here. What about solving the system? Can you get what will be happening into the bars of the system? I solved the system, and then when applying this, you see that some bar revealing with no effort appearing on the system. Once again, graphic statics make it very simple to solve the system. So from this, let's move to the arches and funicular polygon. You know this famous example that has been presented a series of time of Polanyi of 1748. He used the analogy of the hanging chain to define what will be the trajectory of forces that will be inverted as a mirror along this line. So we see that you have a distributed force along the chain. It will drive you to a force here that's going out, that's going out of the line of the thickness of the arch. And if you go more in detail in modeling the concentration of loading on side or in the middle as heavier balls, you can have a new line that is just fitting the inside of the geometry. So that will be becoming later the theory of the truss line. You can see Polanyi working here on the theory of truss line, which came about, 80 years later, 70 years, no, yes, 80 years later with Gerstner, Mosley, and Mary. So let's move to it just to show you that the very beginning of this assessing of arch was coming from Da Vinci, that invented mechanism to check the kinemically collapse of arches, and Bally also is showing the first indication of what will be coming the hinges into arch when an arch is coming to collapse. Again, Leonardo da Vinci with the chord of the external arch that won't cross the internal arches, and Méry that will be proposing the system. What about graphic statics? Graphic statics have been proposed to assess this, and we'll be using the first funicular polygon. So for this, you have to build the load line, as you know already, by denoting and numbing each of the force on both sides. This is known. And the next step will be that your system will be symmetrical, and you will need to place a pole at the middle of it. You have to choose a pole that will be on this line cutting the resultant forces somewhere, and you can start drawing a series of lines. As soon as you have a line, you can draw a parallel on the figure on the left, and you will have the first result. The fact is that as soon as you have three lines, you have your first triangle of forces here, showing that this loading here will be equilibrated by two segments of line of two parts of the arch, and you will get the resulting force from this. So you will be you will have a mean to draw this funicular polygon very easily, and this will provide you the form of the arch. So this is about design, this is about form finding. If you are moving the pole, the line from each of the rays, and these rays are just representing what would be the magnitude of the force in this state of the arch, so they are only horizontal or close to horizontal in the middle, and they are shorter and are becoming longer on both sides. Moving from this, you can move the pole, and you will get other results. You see that if you have a closer pole, you have smaller forces and you have higher arches, and that could be a way to adjust your forces. Actually, the line you have here can be compared to classical form you have in architecture. This is the Achaemenid arches, so going from the ancient time, in which you see that the trajectory here has been very close to a funicular. Actually, we will see that this is kind of elliptical geometry, but that fits very well this trajectory of force. The blue one is the parabol that we have just drawn, and the gray one will be the funicular line with a distributed force along the system that we'll be establishing later. So let's move into the parabola. We can draw parabola with different systems. That's very easy to do it. You have force construction that are the elliptical system I just presented, and you have true construction. In between, the parabola will be the place where the point will be at the same distance between the focus and between a directrix line that will be applied here. So you have more complex theory. What is interesting with parabola is that you know the direction of the tangent on both sides as soon as you see that the tangent will pass at a height that is twice the sag of the arch you have here. So you are able to make a quickly calculation about this. You know the magnitude of forces from the force polygon, and you know the direction very intuitively using this short construction. Let's move to funicular polygon and the first application. If you have a system of three forces, you can build the corresponding polygon of force on the right, and you see that as soon as you will be moving the pole of the system far away from the line of loads, the load line, you will have the force that will be increasing a lot. But the fact is that this is the way you can represent the system equilibrium of the force in a system, in which we have the applied force that will be replaced by the resultant at the center of gravity, and you see appearing the magnitude of forces. Of course, if you want to have smaller force, we will change stuff, as we will see later on. What's about the system? You can assess it in the same way using the funicular polygon, and we see appearing two concepts: the concept of the resultant force and the concept of the closing string. Of course, moving this is a way to start discretizing the loading in the several components, and yet we will have a true arches. What's this figure giving you as an information is that, and I will take a little more complex system that won't be symmetrical, so I won't know what will be the equilibrium force in the reaction on both sides. So we need a tool, and the funicular polygon will be the tool we will need for using this. So I just building the load line, putting a pole somewhere, building a first funicular, and then what's happening is that if I replace the system of forces here by only one force, going from A to D, it means the resultant. I am able to equilibrate the vector AD just using this two-side ray on the fourth polygon. And precisely this force will be this one as lengthened to this point, and this one will be the second here as lengthened here. So we'll have the equilibrium appearing here, and that will give you the point through which passes the line of action of the resultant forces. So that's one of the first uses. If you are doing it with another funicular polygon, for example, in traction, you will have the same kind of result by lengthening the extreme rays of the funicular polygon. Another concept appearing will be the closing string that will be drawn between the intersection point of your funicular and the side of the system. And as soon as you use a parallel that will draw through the pole, you will get a specific point that will give you the repartition of forces on the right on one hand and on the left on the second hand. You can do it for any kind of system with vertical forces. And what about non-vertical forces? As you can see here, these forces are not fully equilibrated, and so you have moving on one side of the system, and this construction of the funicular polygon will help you to define this. So let's construct the load line that is not rectilinear. This is curved. In this case, let's get a pole and get the rays. Let's get the funicular polygon, and let's get the resultant. You have the resultant by lengthened the side system. This time the line of action won't be vertical, but will be parallel to resultant forces. And you have here these resultant forces and this resultant force that will be applied. You can do it with several constructions, you get the same result. But what would be a difference is that as soon as you are using this system and using the closing string, you won't have the same equilibrium. Since indeed the equilibrium of the system won't be only vertical, and the way that an arch will take over this horizontal force on one side, or with the hanging chain taking this horizontal force on the other side, won't give you the same result. So we have to be careful about this. So we are back to this topic of the basis, the fundamental of graphic statics, and we'll go more and more in detail about all the application we can have with this structure. So let's have some word to finish this topic about arches. We'll have to discuss 3 topics yet, and then be moving to BIM, and then go progressively to more and more complex system. What about the geometry of arch? You know that you can use the 2 tools we have. On one side, on the left, you have the space diagram, and on the right, you have the force polygon. So you can go from the geometry, so from the space diagram to the force polygon, or you can go from the force polygon to go to the geometry. Going from the force polygon to geometry is from finding, and in the another sense, going for the geometry to the force polygon will help you to have the information about what could be the play of loading you are using of a structure. Here you have 3 different geometry. You have the arc of circle as a yellow, you have a parabola as a black, and you have a funicular, true funicular with the distributed load as a gray system. You can see here which are the system of force, and you can see that it's quite easy to equate with loading. A parabola in which we have just distributed loads on the horizontal. You could have here on the left the force that have to be applied to equate this geometry, but about an arc of a circle, you see that's quite complicated. So you know the orientation of each of these vectors by drawing parallel to each of the line segment of this line. And so it shows you that this figure is very hard to be equated, and you have a force that is nearly infinite on the side. And in any case, that you will need more forces on side to equate such a system. So it explains why this is not widely used in cathedral, for instance, in the last time, and that you will have device as a flying buttress on both sides to create the system. What can be seen more about all this in that actually this arc of circle is perfect to create forces that have to be applied on it toward the center of an arc circle. And for instance, this will be the perfect case for dams, so retaining water, in which you have the pressure that will be perpendicular to the side. If you go to a cathedral geometry, you have a pointed arch. So this is Saint-Denis in Paris. And as you can see, you have arc of circle. You can equilibrate quite easily arc of a circle on the left, on the right, with two different systems. You can see if you divide just the applied force at equal distance, we need more and more important forces on both sides on the right. And if this is the load, so this is a case of an arch, for instance, and in the case of vaulting, you will have to distribute forces all along the arch, and you see that these loadings are growing when you are going on the side. And actually, again, you will have the difficulties when your line is getting vertical on both sides, so you have to interrupt it just before, and using, for instance, flying buttress to create these forces. You can use also this kind of system, and if I'm drawing a kind of pressure, it don't make sense. It's just for the exercise, you see that it's not closed, but this will reveal that you will need another forces in the middle. And that's the case also with the pointed arch we have seen in before. And one of these applications, if this could be what is called the hanging keystone, that is an additional loading at the very middle of the arches. You have example of several approaches. This will be in Paris also, in Saint-Laurent and Saint-Eustache on the right, that will give you element of equilibrium. So let's try to summarize about geometry. You see that graphic statics providing you a very efficient geometry, as well as a parabola if you have a distributed loading on the horizontal, or if you have, as a hanging chain, if you have a distributed loading around the system. You can see that in history, you will have very few examples of a parabola. I will show one actually, but most of the time you will be using elliptical arches, ogival arches, or semicircular arches. Semicircular arches won't be good at all, but you see that using the ogival arches and the elliptical arch, you will get a good approximation of the parabola or the hanging chain, and the hanging chain will be approximated by a parabola if you need so for geometry. So let's move on. Here you have an example in which you have a parabolic line for the arches, but it's quite unique. It is in the 13th century. And what's meaningful is that when you are building a kind of approximation using elliptical curve, you have a very simple procedure that is based on the Pythagorean triangle here that can be built with very simple measure. You have 3 here, 4 here, and you have 5 on the last system. As soon as you have here, you can draw this arc of a circle, and the second one will be drawn from the summit here to have the last circle. So that's a connection in between geometry and funicular. Let's have a word about vault analysis with graphic statics. You can have a series of examples here in which you can recognize the thrust line and the force polygon. At the very end of the 19th century and beginning of the 20th century, you have a series of examples of that kind that have been promoted to assess the equilibrium of arches. And from the principle of Mary that will be only demonstrated with the principle of plastic design, as soon as you have this truss line remaining into the thickness of the arch of the flying buttress here, you are able to guarantee the equilibrium, and resultant forces, as we have seen, are just flowing into the thickness of walls. So let's move on progressively with something else and have some words about what will be the question of using loadings. Of course, to have this equilibrium possible, you have two ways to do it. You have to change the geometry around the truss line, or you have to put some more loading at some places. And this is a classical example in which on the both sides of vaulting, you will be adding earth of even concrete later to stabilize this vaulting. And we can discuss this more in detail with the next slides. And this slide will be the question about designing with masses, and it means loading and equilibrium. If you are just drawing this funicular line drawn with graphic statics inside pointed arches, you see that this line is very close. And this is the minimal thickness you could have with in between the two sides of this vaulting. And this demonstrates that this figure using regular stones on sides and a pointed, a particular keystone in the middle will enable you with how to say that, with a regular geometry to approach very well the ideal first line. You can see also using loading this kind that if you are just trying to equilibrate, as we have seen this semicircular arches here, you have a truss line that is going outside of the line. But using the self-weight here and more precisely the way that will be applied as a backfill on the arches, you will have a new funicular polygon here that will be remaining into the geometry. So this is a case in which you are using the loadings on the structure to make it have a good equilibrium. There are more examples about using loading. For example, if you have the loading that will be associated with the arch in black, and you will be adding what additional force on both sides, you will see that the truss line, the funicular polygon being in dashed line here, will be changed with the yellow one, and the yellow one is getting outside of the arch. So what could be a solution is to have more loaded arches, so heavier arches. You can have a new funicular polygon that will be less reacting to the applied forces here. And as you can see, this kind, the resultant of this force will be less important and could remain inside the thickness of the arch. So that's an example in which using dead load, self-weight of the structure could be an important point. And I remind you that the book from Stevin in 1905 was named with something like the art of using loading, the weighting of element to get equilibrium. There's another example coming from practice from Robert Maillard. This is the foundation blocks of the Saginaw-Tobel Bridge. You see that the problem in such arch is that you have quite two horizontal reaction force. And if you are just pushing in this direction, you have something that's too horizontal to be supported by the ground. So the strategy will be that you have to change the direction of these forces. And what has been classically used in classical masonry bridge is that you will be combining this truss line with the weight of massive block foundation. So you have first change of direction here and the second change of direction here that will give you a new direction for the forces. And this one is less horizontal, more vertical, and this one can be sustained this time about the structure. So this is about playing with loading to equilibrate the system. If you are drawing an arch that has a certain thickness, you can have a thrust line that is running anywhere into the system and you cannot decide. But as soon as you will be developing specific device that will be hinges into the arch, one central hinges and two side hinges, you have to draw the thrust line passing through these hinges, and this will decide where the line of action will have to pass through on both sides and in the middle. This can be explained since the thrust line is a pressure, a direction of forces, and in hinges you cannot sustain bending forces. So it means that you cannot have this distance between the hinge and between the trajectory of forces to make bending appear. So it shows that a thrust line has to pass through these two supports. So let's move on now with the theory of beam and the beam analysis with graphic statics. You will see that with graphic statics, you will have a very powerful tool to assess this. And you know intuitively that from the arch, as soon as you can support here vertical and horizontal forces, you can equilibrate a thrust line into a system. The fact is that if it remains quite flat, the horizontal force will be very important, as we have seen in the Vesey bridge from Robert Maillard, and you are not sure that the support won't be moving. In this case, something happened, and you will need these tension forces below the beam to equilibrate the system. And this will drive you to bending system. So first we have to establish what would be the way to solve it with the algebraical way, and then show the corresponding approach with graphic statics. You have here a series of forces that will be applied to a beam. There is missing support. This is a sliding support on the right, so supporting forces. This disappear. I'm sorry for this. And if you want to make the equilibrium, you know that you have three components of forces, one vertical, one horizontal, and one vertical here. And you have three possibilities of movement, as we have seen: translation, horizontally, vertically, and rotation. So you have three components of forces. If you are trying to solve the system, you will use the equation linked to these three possibilities of movement for bending forces, for example. What about, so this procedure drives you from a moment around the point here to define what will be the reaction force E on the left side, considering the respective contribution of all these forces. That can be done easily with graphic statics. I will show you about reaction forces. What about internal forces? Internal forces are the same as external force. We'll have the same component. You need a horizontal equilibrium, a vertical equilibrium, and you have a rotational equilibrium. About horizontal equilibrium, since you don't have about the horizontal equilibrium, since you don't have horizontal forces that will be applied, this component will equal 0. So there are two forces remaining. You will have the vertical equilibrium that will be sustained by shear forces, and you have the rotational equilibrium that will be guaranteed by inner bending forces. You can use these two equations, the horizontal, the vertical equilibrium, and the rotational equilibrium, to sketch what would be the forces. And for instance, here you have the example that will be managed with a rotation. Rotational equilibrium. This is called the bending forces, the moment of force around this point. You can see that you have this force having no lever arm, this force having one lever arm, XAB, and the third force, reaction force, that will have a lever arm, XRE. And so this system of force has to be equilibrated for bending. So you can write an equation in which you have bending that will be expressed with lever arm of the two other forces. We'll see what is the corresponding graphic statics just later on. The fact is that you have to write an equilibrium equation for each of the interval between two forces. It gives you one equation, two equation, three equation, 4 and 5 equation. And you have to write this equilibrium each time you want to have the direction of these forces. And this force, as we can already see, is very close to a funicular polygon. So let's move on. About shear forces, you can do the same equation, and we have 5 different lines that will be describing each time the equilibrium of the system. So you will need 5 times the same equation, since all these 4 are not present in all the equation. So let's move on to graphic statics. If you have a pure beam with one applied forces, you can build funicular polygon by choosing somewhere a pole, and you have 3 rays that give you the orientation. As soon as you are using here the closing string and you are drawing the parallel to the closing string passing through the pole, we will get what will be the reaction force on the right and what would be the reaction force on the left. So that's the way that the system can be solved with graphic statics, very simply. You see that this geometry is not totally proper compared to this one with horizontal line. So you can use a specific process in which we'll be changing the direction of the force. You just need here to draw what would be the closing string horizontally by this point C that you know, to put somewhere the new pole and get new rays that give you the new orientation of both sides. And that will be revealing the bending forces as we can see before, just after. So let's move on about the same equilibrium with graphic statics. We have a funicular line here hanging below, let's say, a strut, stabilizing both sides, or just a construction line. If you want to make the same equilibrium of this system of force with a pole somewhere, you can cut into the system and make exactly the same equilibrium of forces. So what you have as force will be the force acting here around this point as the reaction force about this applied force and about the component that could be a part of the bending force applied to this line. For this, you have to take the horizontal component and the lever arm that will be perpendicular, and in this case it will be vertical. And so it shows you an equation in which we have this force with its lever arm and this force with its lever arm that will be equated with the horizontal component of the funicular line. So it will show you that this is exactly the same equation you have when you were demonstrating the bending forces. So to have the value of these bending forces, you just need to know the horizontal component of the force along this funicular once it has been drawn, and to multiply by a distance you have here. And about the form of this bending diagram, you have directly the look of this diagram that will be provided by the funicular polygon. And so for calculate force, you just need to have a pole somewhere on an horizontal if your system is just symmetrical, and you have to draw all the rays, build the funicular polygon, and when you are looking to this, you see where is situated the maximum bending forces. You have to take the distance between the beams and the diagram as y here, and multiply by the horizontal distance that can be found here in the force between the point from the pole and the load line. And so this gives you the appearance of bending. That's very, very easy. So let's move to the shear force, this is exactly the same to apply to it. If your system is Q, this is exactly the same. You can demonstrate the same equation and get the same result for calculating all this. So that's a link between graphic statics and funicular polygon and bending forces, and also shear forces. Let's move on to the truss analysis, and then we'll be ready to go to more complex topics and application in terms of design. If you have very simple trusses, you can see that there are singularities, things that are quite special about this. You know that these are hinge systems, so if you are pushing here, you are crossing a perpendicular bar, so you cannot transmit a force through this bar to here below. If you are using this system, you have applied your forces, and you see that this panel named 1 and this force named AB have a connection in which we have A that will be quite close to 1, and at the end what you can see is that A will be equal to 1 in the construction forces. You have to do this preliminary exercise to each trusses. For this case here, we have just a vertical reaction on the right, and you have two bar connecting to this. If you have just a vertical force here, you cannot have a horizontal force here. So you can decide that this bar won't be active and active. So it will give you a solution quite easily as soon as you know that A equal 1 and that 2 equal 3, you will be able to quickly build this force polygon that will be demonstrating what would be the forces, their magnitude, and also their direction, compression or traction in the truss line. So you have two examples in which you have a diagonal that will be compressed or diagonal that will be in tension. You can see here indeed that you cannot have forces in a member C4 or 4C, so C equal 4 and equal 1, telling you that you won't have forces into it. Of course, this is an equilibrium system, as if you have something else that vertical forces here, you will need this bar to get the equilibrium. And this is the same here. If you put a force here, we need this bar that will be working. And if you have lateral force, you will need all this bar to get the equilibrium. So this is the theory as proposed by Cremona, and you can do it more complex with the same analysis. Here, no force, here, no force, here, no force, here, no force, no force here, and here, no force, and you can build the corresponding force polygon. This polygon enable you with the same kind of notation. You know, if I take this node turning in clockwise, I will have B2, 3, and B2, 3 is pushing that direction, showing that this bar will be in compression. And you can assess which bar in compressed or in tension, and this polygon will show you what would be the measure magnitude you're in forces in the system, and in this case the longer bar correspond to a 5, so 1 5 3 no, not 1 5 isn't working that way. 1 2 here with the length 1 2, so this is 1 2, the more compressed bar, and the same occurs in 2E. That would be not 2E is equal 1, so 2 1, and you have to measure forces in the bar, in this bar appearing here. So that's the way that graphic statics is able to solve trusses. And if you could, for this example, decide what could be compressed or tension, this is not that easy with an unsymmetric system in which we have bar, you can know that this is compression and this is tension, but what about the system in the middle? Going to the solving of this truss, we show you where the bar are changing direction. So diagonal will be equal 0 here, and diagonal with change of sign becoming tension. Hence, it was compression in the very beginning. So that's the approach. At the end, you have a system that you can solve completely, and that's a kind of summary before going to applied cases and hypostatic cases, in which you have a kind of a truss that will be inclined, that can be considered as a beam. If you are using a funicular polygon for just the equivalent beam, you can have the reaction force provided by these forces, and you can have this funicular polygon showing you what will be the distance and the force that will provide you with what are the bending forces. If you are going to Cremona, you are able to demonstrate what will be the magnitude of each force. So I remind you that you just have to measure them on the polygon to get the result, and you have the geometry here with what has been the resultant forces in tension or compression. So that's for the very basic aspect of static graphics. Now we'll be moving to two other explanation about what's happening with hypostatic stresses, and this had been prepared with Jean-François Rondeau, PhD, having finished in 2019 in the team. So let's go to a very complex force trusses, and hence a very complex force polygon. You cannot decide what is precisely the magnitude of all of this force in this force polygon if you are looking to the form polygon here, since you have a static indeterminacy of the system in the form polygon. So how to solve this? I remind you that these systems are pin jointed. So in this case, the joints are just turning around the system, and the crossing bar are not hinged and not connected here in between. So they are just bars. First is to decide what will be the level of the hypostatic problem. So you have two formula, one putting forward what would be the level of indeterminacy. For this, you will be using 2 times the number of vertices, so point, the number of bars, and the number of equilibrium you have. This is done for, on one side, the form polygon, and on the other side with the force polygon. And this is equivalent also to another system in which we have the number of mechanisms appearing and the number of self-stresses appearing in the equation. And you know that this level of hypostaticity for the form polygon and from the force polygon has to be equal to mean 2. So in this case, we are able to show that this structure with this connected bar, so connection are here shown by a small circle, need to have 2 self-stresses since you don't have mechanism into the structure. So these 2 self-stress have to be provided or founded to decide what will be the equilibrium in such a frame. So here you can see, for example, one first self-stress that will be applied in the structure as a form of tension that will be applied along the bar number 6, and with the first equilibrium that will be resulting on the connecting nodes. If you are looking to the force polygon, you can see that indeed this self-stress as a tension on a bar here will be equated with 2 vectors coming from each of these forces. If you solve this, you know that having compression here and tension here, you will need compression on the other bars, and tension to equilibrate the system. And we'll have on the complete force diagram what will be the component that will be linked to these forces. So you will need another combination, self-stress as a two compressed bar here. And this time you have a closed cycle of force that will be on tension to equilibrate them. And you will have the corresponding force polygon. So this is self-stress 1, self-stress 2, and you have stress also occurring from the system with the applied forces. So you can see you have several supporters with different direction and one force that will be applied here, and you will be composing all this system when retrieving this force. And actually what has been done with applying force can be connected with the force that will have been applying on the previous slide. So at the end, such a problem would be a combination of self-stresses 1 and 2, and the stresses coming from the applied forces here, and your result can be tuned in that way. Just the fact is that if you are just remaining in elastic analysis, you have to tune all these forces to fit the equilibrium of the tree together. And so this is quite a complicated exercise in which you can scale the different components. So this is the resulting force polygon that can be scaled in different way, leading to different exercises, leading to different results according to what will be put as forces. And there's somewhere a minimum about the collapse force that has to be found if you are looking for the collapse mechanism. You have several examples, and you see that some point could be moved along several lines, and that will be the way we will be defining the system. I'm moving to a series of different cases that can be all fitting this system. You see a whole range of force polygon that could be connected to this very complex system. And you can see that one of them will give a maximum for what can be the collapse load that can be supported. And that will be the final solution. As you cannot do this just that way, you could enter an optimization process. And for this, I will take another example in which we will be defining the system here of a complex trusses that will be summarized here as a form polygon and a force polygon. And you will see from this how you can play with several parameters that will be linked to the problem. This could be made in an automatic way with a process that will be linked to optimization. And you can see that the force polygon is getting smaller and smaller and smaller. And at the end, that will be adjusted for this. And this is the final solution, as you can see here. So if you want to go to analysis, make a difference with design. I will discuss design just after. If you want to go to analysis, you have to enter these different independent self-stress state and assemble them in force polygon and be running an optimization process to get what will be the final result. If you want to take this problem by the way of design, you can force several forces into the system, either by giving the thickness of the bar, or either by imposing what will be the inner stress state, and that will drive you to another system that won't be a minimal, but that will be a choice that could be implemented as you want on a structure. And this is the question of design. So you see that to summarize this, static indeterminacy is just combination of independent force diagram that you have a parametric way to propose this with geometrical freedom, interdependency, and optimization procedure. And you can go to limit state analysis for this example. And in the research led by Jean-François Rondeau, there was validation on this using the kinematic limit analysis on the principle of plastic design that I won't address here. What now about hyperstatic rigid frame with graphic statics? So the root of this theory is that you cannot be maintained only on solid system, and you have to consider deformation of the system. So the place where you will be applying force along the line of action will be important for your solving the system, and you will have a different result if you don't address it properly. We know from the work from Otto Mohr in 1868 that you can find the deformation of a beam by integrating the bending diagram. So the first, to get the bending diagram, you see that you need a double mathematical integral of the loadings, and it provides you the bending of forces. And once you have this result, so this can be done with a funicular polygon. And once this is being done, you can do another integration, mathematical integration on the bending forces and integrating EI. So it means the inertia of the member and the Young's modulus describing the deformation of beams. And so in this case, using again a funicular polygon, you can have the result. And this is what has been done here. You have the first funicular polygon that has been defined with loading applied in the very middle. From this, you will be considering the surface of each of the sliced funicular polygon to have new loading that will be used to build another funicular polygon that will be corresponding to the deformation. And on the fourth polygon for this second iteration, you have to consider EI, so the multiplication between the inertia and the Young's modulus. So you have a way using graphic statics to get the deformation of a system. This has been applied by Wolfis in 1921 and even earlier, as I will be showing just after. And this will be a trial and assess procedure. You know that the funicular polygon will be resulting from the system of forces here. And if you have hinges on both sides of the beam, you just have the support that will be corresponding to this. And from the chord here to the maximum sag of the line, you will have the magnitude of bending forces. As early that you have fixed and on both sides, you will have contribution bending that will be balanced in between the embedding on both sides and bending force in the middle. For this, you will have to place the closing line that will be here somewhere. And the fact is that you cannot decide what will be the balance of the two surfaces here. So what Wolfis is doing is that he will choose a first closing string to draw a first to integrate the system in a first deformation funicular polygon. And you see that at the end, the direction of the last line gives you an angle as it should be horizontal. It should be horizontal since you have embedded line, embedded ends, but here you have a result. So it gives you an angle at the end. So that's not the proper solution. We'll try with another polygon here below and do exactly the same. And you have here the deformation built as a funicular polygon, and you have this time a deformation in the other sense. The true solution is in between, somewhere else. And you can see here that it will be drawing a line corresponding to each of these deformations. So deformation W1 here and W2 here, and will be make a graphical interpolation in between and define what would be the point through which the actual closing string will have to pass through, and defining what will be the balance of bending force in between the support and in between the main span. So that's the trial and essay method that has been used by Wolfie. Wolfie applied also on portal frames, so you can see that you can describe the system of portal frames with two side spans as a simple beam, continuous beam. So you are just making the support column rotating to become horizontal, and the sum of bending force that will be met in the column and in the side span will be presented as the side span of a hypostatic structure. So from them, you see the same procedure with the two deviation, the integration that will be made to solve, and getting the result, then balancing the force according to the respective stiffness between the side span and the column span. So that's for solving in the framework of analysis of the system. Actually, there are several approaches that will be followed once we have a réunion after Simon Stevin defined what would be the rules of graphic statistics that will be founded through the book of Carl Kuhlmann in 1864. There will be several contributions that will drive you to solve this system. First, we have Otto Moore with the elastic curves and on continuous beam, and his work will be detailed on one side by William Wolfie, the approach we have seen just before, and also by William Ritter, his pupil that will be the teacher of Robert Maillard. And the technique will be more and more let's say fitted, not fitted, but developed. That's the word, will be developed by Ritter to get finally the final contribution from Anne Sutter in 1916 that will be proposing the fixed point method. And I will give you an overview since the technique will be used by Robert Maillard for at least one bridge in Bern in 1938. So what's the principle? We have to define what would be a fixed point along the structure through which we have to make a line passing through for constructing graphically the balance of force between the several span that will be met for this system. It can be done graphically as here, and this can be done also with an algebraic process. Then you will be assessing what would be the propagation of bending forces along the span by using this result in which you are just using crossing line that will give you the intersection with the vertical line passing through the fixed point to get this point through which you will have the first diagram. Then you will have to propagate all these forces in between all the terms, and that will give you to produce several closing strings that will be defined the final state of the system. And of course, you will have to take into account the rigidity, so the stiffness of the bars as well of the several span and as well of the column to define this system. You can see that it can become very complex, and here you have the full graphical solving of the problem in terms of analysis. So this is hypostatic analysis, and the bases are the same as you will be using in algebraic method. The only difference will be that we will be using a graphical construction to define this, and you will be proceeding to the integration using funicular polygon. As an example, you have here a bridge that I was mentioning before that will be built by Maya in the Weissensteinstrasse overpass. And for this, you can see the same process in which we have already a geometry. So this is the sign that there have been studies before to get a form. So this is analysis and not exactly anymore design. And you can see here the bending force appearing through the several deformation and propagating. You can see also the fixed point that are here and here, and the trial, or the trial, but the intermediate closing string that has been used to define this line plus this line, giving the final closing string that will give you what will be the true appearance of the funicular, since indeed they are just funicular here that will be cut by the specific line. So this is the solving, and Maya will be using an algebraical procedure to define what would be each step of the process. And the result is here. For using graphic static for hyperstatic system. So what's about 3D graphic static? Just short rule telling that you have to approach the polygon-based and the vector-based approach. This will be explained for the vector-based approach in the next week, and you will have 2 lectures from Masoud Akbarzadeh that will be presenting more in detail the polygon-based approach in some weeks. About the vector-based approach, the topics is about assembling this contribution of each node into a complex 3D graph, but this will be explained next week. No, we have covered all what's theoretical, and we can move to 2 examples of application of graphic statics for design. The first that will just be shown is an example that has been designed by Jörg Kronzett, so the Swiss engineer, in 2005, the Traversinger Steinweg number 2, and this is the bridge. This is a hanging bridge between 2 rock wall, and you can see a funicular line, a funicular cable that will be suspending other cables that themselves will be hanging what would be the deck or the floor of this bridge, starting from here and finishing here. You can find the first design of the geometry of this funicular hanging bridges was a funicular here, and you recognize what would be the rays of the funicular polygon. At the end, you will see that you have a series of flows that will be applied here that will be equilibrated by 2 segments of the lower truss line and with the hanging arch here. And you can see indeed this closed cycle of force in which we have the applied force about the direction of the hanging, and this hanging will be equilibrated by the support line. So these are the forces in the hanging line, and these are the forces in the successive segment of the lower funicular. Working on this, there will be graphical construction to define what would be the ideal direction of each of the suspended forces. And also your concept would see that using skew or diagonal hanger for each of this loading here, we put additional tension forces on the several funicula that will help to stabilize the system and enhance the quality of the equilibrium. So you will see here an adapted force polygon and form polygon for this example. Your concept, so just to show you that the pre-stressing can be represented also by a closed force polygon here. Just to say about this result, so this is about design, and graphic statics help you to define the geometry. Your concept also use it for analysis in the framework of strain and tie on a building designed by Adalberto Libera and Sergio Musmecci in 1944. And you can see again the force polygon and the spatial diagram from polygon as applied in pencil on this figure for this building. So let's move for the last example that will take again 20 minutes, and then I will answer a question. There are two examples of design as managed by Robert Maillat. So Robert Maillat, I haven't presented. That's an engineer having worked in between born in 1872 and died in 1940, that will be the one reinventing totally the form in concrete, and we'll be using graphic statics. These are figures on the right. These are working drawing showing that there are thrust line, funicular polygons, and a force polygon here that will be used with several successive drawings to define what would be the line of the arch. And you see that according this line and considering the transversal section with its own inertia that will influence the level of the central gravity. Considering all these aspects, he will be drawing again and again several times the lines of the lower chord of this bridge. So we'll be using in an interactive approach graphic static to design the geometry of the forces. Of course, there are other drawing just for analysis, but I will be focusing here on graphic statics for design. So this is the bridge that you know already, and you will be for first analyzing purposes. I will be discussing design just after. So for analysis purpose, I will be slicing this bridge and calculating what are the corresponding loading of each of these bridges and start building a load line. The load line is here, and I will start building a first funicular polygon acting in tension by just deciding that I will use the side rays that will have an angle of 45 degrees, and that will help a lot for the solving thereafter. So you have a pole, we have the first ray, and you can build, as you know, all this ray and the corresponding funicular polygon. Once this has been made, you can be looking for the resultant forces. So the resultant is this vector starting from 1, finishing with 21. And you can just lengthen this line on both sides to get the intersection. The fact is that since he decided to have 45 degrees for each of this line, we have not to make complicated drawing to have the tangent. You know that starting from the head, it's just 45 degrees and you get this intersection point. You know the equilibrium of three forces. You have here the resultant and here the two side rays, but you can also try to find what would be the reaction forces at the middle and at the side. What you know is that the system is symmetrical. Actually, it's not symmetrical, but it's quite similar to symmetrical and hence horizontal line here. We can demonstrate this is equivalent. And you know that the line of action that will be starting from the middle will be horizontal. It has to be equilibrated with this line of action from the resultant forces and equilibrated also with the line that will be coming from the support. So you're just drawing this horizontal line, intersect the line of action of the vertical force, and you know that the third line has to pass through the hinge and through this point. So you know this direction, and you are able to calculate the forces on the support formation. But you have also the direction of the first ray, the tangent to the funicular polygon, that will be explaining what will be the thrust line all along the arch. So you keep this direction here and you keep this direction here, and we'll have a new funicular polygon that will be appearing. There are two polygons, since there are one considering only dead load and the other considering dead load and half of the life load. I won't enter into detail, but what you can see is that this direction here, this direction here and this direction here give you the pole that enable to start with the rays that will enable you to draw the first line into the arch. And this first line can be compared in the position with the position of the center of gravity. And where these points are not the same, we have small lever arm that will give you directly what would be the bending forces along the arch. If we have already tried to calculate bending force in such an arch with classical algebraic method, you know that's quite complicated and it's quite immediate as a result when you are using this one. From that, calculating the support and also bending force. But you can take it also from the side of design. And in this case, you just have the line of action of the loading. You can take a first loading and you will be building the construction as you know. You get the pole and the direction from the support and start building this truss line. And once you have this truss line, you can balance the successive section of the arch and of the deck to correspond to the line of to correspond to the truss line. So that's the way this approach has been used in the very first step of this drawing from Maya. So that's for the first example, and I am able to demonstrate indeed from the successive drawing that has been made for solving the system. And that's the result. So you need, you know, everything you need to design this bridge, calculate the forces and so on using graphic statics. This is not more complicated than this. So I will be moving to the last example of the Chiasso shed. So this is the shed that has been built in front of a warehouse. This warehouse is situated between two railways. So we have one on one side and the other here. The third one being here in the basis of the slope. And you see that this building have a regular system of columns in which Maya will be implementing the system of mushroom slabs. I won't discuss this during this lecture. These are other topics yet. And so from this, you can see that Maya will be implementing two stuff. The first will be two principles, I have to say. The first is about implementing a bending stiffness mechanism with the roof. Actually, the actual roof is this one with rib and with the hanging funicular line below. And the second system that the geometry has to be aligned on several lines. I will be discussing this. You see that Maya with the first sketch is using very simple mechanism. You have two flange of 1 meter, you have a thickness of 10 centimeter, and you need a rib below of a 24 centimeter on the horizontal line and 30 on the vertical line to get the neutral axis just at the limit of 10 centimeters. And you will have another line here, just minimal 20 centimeter to be able to have the tension reinforcement into it, passing through. At the end, you will have a kind of rounding, as Maya do it very frequently on each of the bridges using a parabolic line, so you know how to draw a parabolic line, and to have a stiffening member. So this is the principle it will be developed in the same moment for stiffened R bridge, in which you have the deck that will be quite stiff and an arch that will be perfectly funicular. So this is the same principle that will guarantee that you can support, that you can sustain bending force into it. So now what about the geometry? You see that the top of the roof is just at the limit of the floor of the third floor. You have the lower part of the funicular will be just at the top of the lower floor. So these are the limit for the geometry. And we see that the dividing struts will be half of the span you have in between two columns. So you have a kind of graphical system in which you have to place yourself to design a structure. So first you want to draw a funicular line. You would like to have a funicular line that would be horizontal in the middle. And if you do so, you have to have in mind that this funicular line will be equivalent to these two lines of the roof. So you are building a load line in which from the corresponding letter, you will do parallel to the roof. And you have to connect to the rays that will give you the geometry of the funicular line. So if you know this line and you know that this had to be horizontal, you can draw from the middle of the load line horizontal line that gives you this point. From this, you will be drawing this line corresponding to each of the vertical struts. And from the intersection, we'll get all these rays of the funicular line, and you can draw it on the figure. You can see that this is too low, and as soon as you want to make this higher, the geometry will show you that you will have a lower point here. So this lower point normally has to be above the floor or the second floor. So you will be moving this line, this point here. This point here is defined. If you draw this line, you know it will be parallel to the middle line of the first line. So this direction here will be known from the pole, and you can draw this vertical line and define what would be the successive ways of the funicular polygon. I'm just comparing the geometry, and you see that for up to here, up to here, you have this geometry that will be fitting perfectly the line of the actual structure, and with the lower point being here. What will be changing is here, and that's an expansion for this I will be explaining right now. If you are trying to connect this structure with the column here, you have to build another force polygon here. I will just define it as being vertically. I know this direction here, and here. So parallel here giving that line, a parallel here giving that line. So I know the intersection point here, and I know this direction here giving the third line. So you see that if you want to connect this force polygon and this one, I have to move this funicular polygon on the force polygon to get O being corresponding to P. So I'm doing this, and what's happening is that I can see what will be the resulting forces along the column. You can see here from A to P what would be the direction of force, and it's going outside the column. So it means that you have huge bending forces and that you have a problem of equilibrium for the support. What can I do? I can having true discussion about this first polygon and trying to have different direction. If I'm imposing a new direction, that would be more steep and even more steep to remain inside the line, you can see the geometry of this ray between A and N that is changing. So what I'm doing now is that I will impose the line from the very limit here, 15 centimeters at the head and on the lower part. I have this direction that I will be imposing on the force polygon. And if I just connect this, I have a new direction from that line that is not anymore getting an intersection on the symmetrical axis. So I will be prolong this line to here and correct this line through. I'm doing this here, and to be for it to be connected, I have to change the final line of this line section here to get the equilibrium being perfect between the column and between the first ray. And curiously, I'm stopping here. You can see that here I haven't changed the direction of the line on the side here, and my arm won't go further since the line are fixed. But what's the problem? There will be bending. Of course, there will be bending. And of course, the system has been thought as a stiffness member. So what you can see is that indeed bending forces are running along the roof that will be the stiffening member, but also the beam that has been designed on a T-beam with stiffening in the inner center. And you see bending running into it. You can see that you have small problem of bending all around this. And if you want to make this bending equal 0, you know that bending is just the direction of forces divided by the deviation. So why not correcting the geometry? So in yellow, you can see the geometry as below, and I have exaggerated the correction of the geometry. Actually, this drawing is made at a scale of 1 centimeter, 1 centimeter corresponding to so 150. And so the correction is maximum 5 centimeter. And if you draw it at scale, 5 centimeter at scale on the drawing correspond to 1 millimeter. So we cannot adjust the geometry to make this force getting to 0. So you have to sustain bending. This is why the system has been led in that way. And that's the way that graphic statics has been used for this iconic building from Robert Maillard in 1924. So this is the end of my talk. I have a conclusion, but I see that we will be lacking time and not leaving time for the question for all this. So this will be the end of my talk, and I thank you for your very kind attention.